Hi, everyone. My name is Ken Liu. I am a physics master student at San Francisco State University, and my research is on gamma ray burst. I am carrying out this research with Dr. Nicole Lloyd-Ronning and Dr. Roseanne Cheng at Los Alamos National Laboratory. The main goal of the research is to try to understand the underlying physics of gamma ray bursts and the progenitor system that produces them. And such physics leads to important questions such as which stars make a gamma ray burst and why. Gamma ray bursts are the most luminous objects in the universe. The duration of the prompt gamma ray emission is a signature of how long a relativistic jet lasts during the black hole accretion disk system that powers gamma ray bursts. And this quantity provides information about the amount of mass in the disk and the angular momentum in the black hole disk system. And importantly, it is linked to the properties of the progenitor system. Until now, primarily single massive star collapses have been considered as these progenitors. Using MESA simulations of interacting binaries, we examine the possibility that longer-lasting gamma ray bursts result from a massive star that collapses in an interacting binary system, which can provide the resultant black hole disk system with more angular momentum and therefore a longer-lived and more powerful jet. Because gamma ray bursts are violent, and through these violent processes, they produce very highly complex physics. To reduce this complexity, we approach our question from a tractable way. We are using an open source code called MESA, which stands for the Modules for Experiments in Stellar Astrophysics. We are using MESA because it provides us the necessary information to further our studies so that we do not have to reinvent the wheel every single time by developing our own code for the hard physics, which is very time consuming. And next slide, I just want to show some of the results of the capabilities of MESA. I start off, this is a study of a binary system with a 14 solar mass star with a 8 solar mass black hole. MESA has the capabilities of allowing me to write in small lines of codes, and it provides us with plenty of information about the physical processes of the system and how it evolves over time. For example, if you take a look at the graph all the way to the right, let me point out right here, it shows how the initial masses start, which is the top panel, and how you can see that the black hole accretes and basically eats up some of the masses from the donor star. And it's a remarkable thing to try to understand such abstract things on your very own laptop. And with MESA, we can set the initial conditions of our physical system in any way we like. We can change the initial masses, the orbital period. This is useful because when we try to simulate nature, this helps us try to understand it a little bit more. And as shown from these graphs, all this is already built into the code, and this is a time saver. And MESA allows me to compute angular momentum of the interacting binary system, a quantity that is very important in working out the progenitor system. We can see how tightly orbiting black holes leads to higher angular momentum of the system. And the easiness of this code allows us to test our ideas quickly. And that is very, very useful when dealing with such a highly technical problem. Thank you for listening.